Dear students, in this lecture, we will discuss about the Thevenin's theorem and we will see how to use Thevenin's theorem to solve a given electrical network. Like any other electrical circuit analysis technique which we have studied, let it be mesh analysis, let it be nodal analysis, or superposition theorem, right? So like these analytical techniques used to solve the electrical networks, Thevenin theorem is also used to solve the complex electrical circuitries. Using Thevenin's theorem, we can convert any complex circuit into a simple circuit. Here we do not have to consider one source at a time. How many number of sources we have in the network, we can take them all at one time and we can convert any given complex electrical circuit into a simple electrical circuit, and then ultimately we can determine the response of the given electrical circuit as required. So they were the inventors of Thevenin's theorem. Now, Thevenin theorem states that if we have any linear bilateral network which contains one or more than one, like in superposition theorem, the condition is that there must be at least two energy sources, right? But here that constraint is not there. We can start with a single source also, means one source must be there in the network. So any linear bilateral network that contains one or more than one energy sources and passive elements. Now passive elements, your resistance, capacitor, inductor, but here we are talking about the resistive circuit only. So we can replace such network which contains energy sources, which contains passive elements, by a simple network. Now, this simple network contains a voltage source. We call this voltage source as Thevenin's voltage given by VTH, and a single resistance known as Thevenin's resistance represented by RTH. Both are connected in series across the load terminals. That means load terminals are not altered. Apart from the load terminals or load resistance, whatever circuit we have, that circuit can be transformed into or converted into a simple network of VTH and RTH across those load terminals. So the voltage source that we have in Thevenin's equivalent is the independent voltage source, which we call as VTH, as already told, and then the resistance we call as RTH, right? This is both are Thevenin parameters basically. So this is what is written here. Now Thevenin's voltage is also known as open circuit voltage. Now we will understand why it is known as open circuit voltage. And the series resistance is known as Thevenin's resistance, which is denoted by RTH here, right? That means if we have to obtain the Thevenin's equivalent of any given complex electrical network, which is linear and bilateral, yes, of course, then we need to have two parameters. These two parameters are must. So that means we need to calculate Thevenin's voltage of the given circuit. We need to calculate Thevenin's resistance of the given circuit. Thevenin's resistance, what is Thevenin's resistance? Thevenin's resistance is nothing but an equivalent resistance. It is an equivalent resistance, but this equivalent resistance is measured in a different manner. Conventionally, we measure equivalent resistance of a network from end to the source. Like if we have a network here, for example, V is the resistance, then this is R, this is also, let us say, R, and this is also R, for example. So how will we measure the equivalent resistance? The equivalent resistance will be measured across these two terminals here, input terminals, right? So that we can find out the value of I, or if I is given, we can find out the value of V. So we will start from this point and we will converge to the input, because we are measuring R equivalent here. So these all three resistances will form R equivalent. So in this case, R equivalent is, so these two are in parallel, R parallel R, and the resultant of these two is in series with this one. So plus R. So this is how generally we measure the uh, what you say, equivalent resistance. But Thevenin's resistance is not measured in this manner. There are certain steps to measure Thevenin's resistance theoretically in the given electrical circuit. Then we have Thevenin's voltage. The Thevenin's voltage is nothing but, no, but an open circuit voltage which is calculated across the open load terminals. That means to calculate Thevenin's voltage, we open the load terminals. If we have a resistance connected across the load terminals, we will remove that load resistance and we make those load terminals open. Now we can understand this whole concept by these schematic diagrams here. For example, you have a complex electric network which is represented by this block. So this may be uh, a network with multiple meshes, multiple nodes, multiple sources, whatever. It is a complex network. It is a linear network, and it is, let us say, bilateral. And these are the load terminals here. And this is our load resistance. Now, this particular part of the network can be replaced by a simple network as per the statement of Thevenin's theorem. And that network contains a VTH, which is known as Thevenin's voltage, and an RTH, which is known as Thevenin's resistance. So this combination of voltage and resistance is the Thevenin's equivalent of this particular circuit. So as you can see, we have not altered the load terminals. They are same, right? Now, let us understand this theorem with the help of a dummy example. So let us consider an electric circuit as shown here, and this electric circuit has a voltage source V and a resistance R1, and then resistance R2 and R3, and then we have a load resistance RL here. A, B are the load terminals. They are the load terminals. Now let us say some current IL is flowing in this branch. Now our purpose is to calculate this load current basically. Okay, so this whole theorem can be implemented on a given electric circuit in 4 steps. The step one is that because we need two circuit parameters, two Thevenin parameters, these two parameters from the network as given here. So let us come back to this circuit. So this part of the network, this complete part, apart from the load resistance, this part will be replaced with a Thevenin's equivalent. The load will remain as it is. So First thing, we need to calculate the Thevenin's resistance. Then we need to calculate the Thevenin's voltage. Then we need to draw the Thevenin's equivalent. And finally, we will calculate the load current if required. Now, why I am saying if required, for example, in this circuit here, I may be given a circuit like this. So the load terminals are already open. So if the load terminals are already open, so we cannot have the current in the load branch, load terminals, right? So if it is asked to you that calculate the load current, then calculate load current. Otherwise, you can leave it up till step 3. Okay, you can stop here also at step 3. Step 4 is only done if IL has to be calculated as per the statement of the question. Let us come to the first step, that how to calculate the Thevenin's resistance. See, now what is Thevenin's resistance? First of all, you understand. Let us come back to this circuit here. And in this circuit, how do we calculate Thevenin's resistance? To calculate Thevenin's resistance, we remove the load branch. Remove this one. And make these terminals open. A and B, make them open. Then whatever energy source you have in the circuit, replace that energy source with its resistance. Replace with resistance, right? So voltage source, ideal voltage source has zero resistance, and ideal current source has infinite resistance, right? So redraw the circuitry. So this is what is explained here. So first of all, we remove the load resistance and make the load terminals open. Ignore if the load terminals are already open. So if they are already open, you don't have anything to remove. So let it be like that. Then in second step, we replace all the energy sources available in the given electrical network with their internal resistances. Now note, in the case of ideal voltage source, because ideal voltage source has zero resistance, so it is replaced with a short path or short circuit. And the ideal current source, which has infinite resistance, is replaced with an open path or open circuit. Okay, so the reason is also explained here. So we have replaced the energy sources with the resistances. We have opened the load terminals. Now we will redraw the circuits. Now redraw the circuit after applying step 1A and 1B. Now this is what we have. Now you can see the original diagram. So this was the original circuit diagram here, this one. And here R1, R3 and R2 are connected across the load terminals. So we have R1, R3 and R2. And now this is what RTH is. That means RTH is calculated from the open load terminals by replacing all the sources with their resistances, right? Now, if we have to calculate this Thevenin's resistance, we can make a small assumption, which is very, uh, which is also not required. If you are very much expert in solving the network, you can easily solve them. But for the sake of simplicity and just for the sake of understanding the concept, let us assume that a virtual voltage is connected here. So this would deliver some current, let us say I dash, for example, some current would be there. So this current will flow through R2, will come to this junction, let us say this is X, and will go into this branch here, will come to this branch here, So, and then these two current will meet at, let us say, junction Y, and then back to this one. This is I dash here. So this is how the current could flow if we have a voltage connected at AB. Now, so we will simplify this network from this end to this end, right? So these two resistances are in parallel, and these are in parallel, and the combination is in series with this one. So RTH in this case is, so RTH in this case is R1 is parallel with R3, which is in series with R2. So this is how you can calculate RTH. We will take one more example just to understand this concept. For example, you have a network like this, and this is your load branch here. This is V, this is R1, this is R2, this is R3. Now, this is the load branch. These are the load terminals AB. Now, if we apply all these steps on this particular network, we can redraw this circuit. So there was a voltage source here. It is shorted. And then we have a resistance. Then we have terminal A. Then we have here terminal B. And we have resistance R2. We have a resistance R3. Now here we are calculating RTH across the open load terminals. Now this is R1. Now what will be the value of RTH here in this case? So RTH in this case is equal to, now you can see, if you connect a voltage here, this current, the current because of this voltage will go in these two branches and will meet here. So that means this R1 is in parallel with the combination of R2 and R3. So R1 is in parallel with the series combination of R1 and R2 and R3. So that means we have to remember the steps. And if we remember these steps while calculating RTH, we will not be wrong in calculating RTH. I'll take one more example. For example, we have a network like this. We have a current source instead of a voltage source, and we have a resistance here, and then we have a resistance here, and we have a resistance here, for example. Now this is our load resistance, right? This is our load resistance. So I'll draw one resistance here also, and this is R1, this is, let us say, R2, this is, let us say, R3. Now, if we apply these steps on this network, so we will open the load terminals. So let us open the load terminals. So I have opened. So these terminals were AB, let us say. So A and B, I have opened them. I have R2 here. I have R3 here. I have R1 here. Now replace the energy sources with the resistances. Now here let us see, current source is replaced with open path. So we will make it open. This is open path now. Now if I connect a voltage source here, so the current will come to this junction, but it will not go here. So that means this R1 is not considered in RTH. It is a redundant branch. We call it as redundant branch. It is not required. So in this case, RTH will be equal to, now the current will flow like this. So both are in series. So R2 plus R3. R1 will not come into scenario. So my purpose was to make you clear, make you understand that how can we calculate the RTH in a given electrical circuit, because electrical circuit may be have any formation. You may be asked to calculate RTH, um, or sorry, you may be asked to calculate load current in any branch of the circuit. So accordingly, your load branch will differ, right? Case to case. Now let us come to the Thevenin's voltage, how to calculate Thevenin's voltage. It is very simple to calculate Thevenin's voltage, which is also known as open circuit voltage. Now to calculate Thevenin's voltage, we remove the load branch and we make the load terminals open. So we measure Thevenin's voltage across these open load terminals, right? So these are the open load terminals. So across these open load terminals, we calculate VTH. Now, because we have calculated VTH across the open load terminals, that is why we also call this voltage as open circuit voltage, or it is denoted by VOC. Now let us calculate VTH here. Now if we consider this to be positive and this to be negative, this is also my assumption. I can take this as positive, this as negative. This is totally up to me, right? Now, so VTH is actually VA, means the voltage at this particular node, minus VB, means the voltage at this particular node. Now, let us say this current is I. Now this is junction X, for example. When this current I will come to this junction, it will not go here, no current. Why? Because these are open. This is an open branch. This is an open branch and no current will be there. Now, so we have no voltage drop here, right? Okay, so this current I will flow through R3 as it is. It will flow through R3 as it is. So that means if we redraw this circuitry here, so that means if we don't have any voltage here, so we can consider this A and B terminal. Let us say this is Y here. So in this case, AB are same as XY. So these are same terminals. So we are measuring VTH here. So that means VTH will be the voltage across XY. So in this case, VTH is equal to Vx minus Vy. Vy is 0 if we consider this to be a reference node. So VTH is equal to Vx. Now Vx, what is Vx? Vx is the current through this R3 and the value of R3. Now that means we need to calculate I here. So I is equal to V by R1 plus R3. So we'll substitute this value here and we can substitute the value of Vx in this equation so that we can get the value of VTH. Now, calculation of VTH may differ from circuit to circuit. It all depends upon where your load branch is located, that you need to take care of, right? Now, third step is that we will draw the Thevenin's equivalent of the given circuit. Now, Thevenin's equivalent is nothing but the two Thevenin's parameter that we obtained in step 1 and step 2. So they will be used here and we will connect both these elements in series with one another and we will keep that load branch as it is. And then we can calculate the load current. Now, how will we calculate the load current here? So we can apply KVL in this thing. So Applying KVL, as per KVL, the load current that comes, the equation is given by here, this particular formula here. IL is equal to VTH divided by RTH plus RL. So applying KVL in this mesh, so let us apply KVL. So if we apply KVL like this clockwise direction, so VTH minus IRTH minus, sorry, not IIL, it was IL, minus ILRL is equal to 0. So now from here we can calculate IL. So IL will be equal to VTH divided by RTH plus RL. So it is the same formula. So that means to apply Thevenin's theorem on any given electrical network which is linear and bilateral, first we need to calculate RTH, Thevenin's resistance. Second, we need to calculate the open circuit voltage. Third, we will draw its equivalent circuit, means the Thevenin's equivalent. And fourth is that we will calculate the load current if required, if it is asked to calculate, right? If it is not asked, then you can stop at step number 3. So this is all about Thevenin's theorem, dear students. Thank you so much.